Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Roberto Jacobazzi. The title for the talks is Interference and Incompleteness, an Abstract Interpretation Perspective. Dr. Jacobazzi received a PhD in computer science in 1993 from University of Pisa. From 1993 to 1995, he was a postdoc at École Polytechnique in the equipe of Patrick and Radler Coast. Back to the University of Pisa as assistant professor in 1995. He moved to the University of Verona as an associate professor in 1998. From 2000 to 2003, he was a full professor in computer science at the University of Verona, where he also served in many different leadership positions, such as provost for education, provost for research, and dean for College of Science and Technology, and also the head of computer science department. From 2016 to 2023, he was also affiliate faculty at the IMDEA Software Institute in Madrid, Spain, with the Cátedra de Excelencia of the Comunidad de Madrid, awarded in 2017. Excuse me for my French thing. From October 2023, he's a full professor at the Department of Computer Science at the University of Arizona. His research interests include abstract interpretation, program analysis and verification, semantics of programming languages, program transformation and optimization, security, computability, history of CS, and lattice theory. He was a co-founder of Julisoft, now part of Grammatech Inc. USA, general chair of the 40th ACM POPL 2013, and member of the steering committee for POPL until 2015 and of major conferences in program analysis and program verification. He was a PI for several international projects in the area of programming languages. He received the Microsoft Research Software Engineering Innovation Foundation Award in 2013, the Facebook Probability and Programming Research Award in 2020, the Amazon Research Award in 2021, and the WhatsApp Research Awards on Privacy-Aware Program Analysis in 2022. He is an ACM Distinguished Member since 2023. Dr. Roberto, it's a great honor to have you as
Thank
part of the
you.
webinar series, and the floor is yours, and you can start your presentation.
Okay, thank you very much. I try to join with my slides, and actually, thank you for inviting me to make this presentation. I'm somehow theoretician, so you will probably find this talk a little bit theoretical, but this is, let's say, the perspective of abstract interpretation is always interesting to know because it gives us some foundations about many issues that happen when you run a code. For instance, information flow, that you have bad information flow from very high private information areas in the memory towards public ones, or whenever you want to protect IP of your software and so on. So having an abstract interpretation perspective is interesting because it allows you to know the limit, what you can do and what you cannot do in this field. So you just explained in this is my automaton actually. So that's me. And you just explained it so we can go through way quicker than I expected. So what does it mean understanding programs? So actually analyzing code. So I put the code on one side. You have two loops, one inside the other, and you have a little tiny image on the right. If you want to just tell me what the code does, it's like asking you what's in the image. So you have to really look carefully inside. So looking carefully in the code means analyzing the code. Analyzing the code means producing all the invariants at each program point in such a way that you can know, for instance, that variable. I don't know if you can check my pointer, you don't, but anyway, for instance, at the beginning of the second while loop, you know that n0 is equal to n, j is bigger and equal than 0, but in particular, I is bigger and equal than j plus 1. So you have many information that you can extract, a lot of information, and all these invariants and all these properties characterize exactly what's happening at that program point when you run the code. This is formal methods. You know that hardly scale. Nowadays, large language models helps a lot to produce these invariants, but with many hallucinations sometimes. So there is an issue inside this. Why it doesn't scale, and in particular, why it's so hard to extract those invariants? Basically, because the way the code is written can completely destroy your capabilities to understand what's going on in the code. This is known as code obfuscation. You have code obfuscation when the way it's written, the code, so the code semantically produces the same effect as the other one. But the way it's written, it's such a way that any algorithm and even any large language model trained in the best possible way may find that code obscure. And this corresponds on the right-hand side to that obscured image. So you cannot really understand if there was a chessboard in that image. It looks like pretty much the very first images of the universe after the Big Bang. So a lot of energy condensed. But no, that's just the same picture as before, just so blurred, just obscured. This happens also in code. So how this happens and why this is important in information flow, in program analysis, and in generating security. So, okay, so we can get back to the very beginning of the history of computation and look at Dijkstra, what she said. Good programs are well structured and have concise invariants. That's exactly what we expect to be a very good, well-written program. But they are very interesting, in particular for security, for avoiding reverse engineering, attacks on the code, or maybe to generate deceptive flows of information that can foil an attacker that tries to catch information from what's happening in the code. And this happens when you obscure the code. So if I take the sentence of Dijkstra and I move it down towards making it difficult to understand my program, so an obscure code should be badly structured, so not well structured, and in particular, it has to have very messy invariants. Okay, so what an attacker does typically, I mean, the code is too big to be attacked by hand. You need to use tools. You need to use tools like disassembler, tracer, decompiler, slicer, SMT solvers, IDA Pro, that is a bunch of tools, emulation, monitoring, dynamic analysis, static analysis, all these interact. And with the code that you want to analyze, you want to attack, for instance, if this is what your goal. And your goal is to produce a proof that some invariant hold at some program point, and you use all those tools to do that. Why you are obliged to use those tools? Because you cannot do that by hand. So an adversary is somehow constrained by using those tools. There are more and more advanced tools coming to the market, but still, each of those tools is an algorithm. So by itself is a tool based on a Turing machine. So it has to be computed by a computer. So it's a set of instructions. So the point is that if I want to obscure, so make my attacker harmless, it's probably enough. I wouldn't say totally enough, but it can be a good strategy to obscure, to make all those tools unable to grasp and to catch the information. So making obscure my original source code. Let's see this with a little example. Dependency and slicing. Slicing is a well-known tool. I use that little machine that actually is a big machine for slicing ham in Italy. And it actually slices the code into pieces of code, so smaller programs, that have a consistent information flow. So the dependencies between these parts of the code is coherent. So you have everything that concerns one variable, for instance. So all the dependencies between that variable and all the others will be collapsed, included within the same slice. That's very helpful because whenever you want to attack a large program and you want to extract, for instance, a cryptographic key, you need to know where that key flows. So you need to extract from that huge program the part of the code that depends or has dependency with that cryptographic key. This tool is very important for for reverse engineering. So let's try to see how to protect my code with respect to the slicing and dependencies and dependency analysis. This program slicing goes back to 1981. So the paper of Weiser is fundamental paper. Then there are many instances of this definition that produce a lot of tools. You take, for instance, this little program, you see that there is a loop, and actually the loop at point 3, it loops forever. And okay, so how does it work, the algorithm? You need an algorithm, so you need to program that tool. So you need to produce something that can be computable. So an approximation of the computation made by the code. And you generate the so-called program dependency graph. The program dependency graph is that one that you can find on the right. You will see that there are dependencies between the entities if there exists a link, so a possible flow from one entity, so one node, to another. And look what's happened. The program dependency graph is completely derived syntactically, so it doesn't concern what really computes the program. Why this? Because you cannot extract all possible infinite traces of execution of one program. In general, properties of programs are undecidable. So you cannot extract in finite time, because the attacker needs a tool that runs in finite time, a complete description of what's happening in my program. So I get an approximated abstraction, I will call it abstraction, of my information flow, which is described by all the paths that you can generate over that dependency graph. The dependency graph so extracted is purely static. And look what happens. You want, for instance, to look what depends upon over the point 4 and variable y. So you want to extract, so it's point 2 and 3 are completely useless. So you can completely subtract from the dependency graph that subgraph and still get back to a smaller piece of code. This is pretty good. How can you do this? You simply remove everything that do not interfere with the variable y. The only variable that interferes with y is x. This is clear, and this is exactly what's happening in any runtime of the program. The point is the following, that how do I build that program dependency graph? I build that statically, as I said. So I start from the entry point, and then I will reach program point 1, and then 2, and then 3, and then 3a, which is the body of my loop, and then I reach the fixed point. You see that this is the graph that I built. So if I build that graph statically, and I take, for instance, another program, like the word count program, you see there are many variables inside. Okay, so the question is, I have variables on the number of lines, number of words, number of characters. This is a little program that counts all these. Okay, so if I want to slice out the part of the code that concerns the number of lines, which are that underlined, then this is the criterion, this is the subcode that I will get out from the slicing. And if I want to slice out the number of words, I get that. And look what's happened. How can I make this algorithm that produced the dependency graph useless? I need to inject into the code fake dependencies. So look what's happened here. I'm adding some predicates that are always true and always false. The first predicate in green is always true. So this is actually an invariant of the code at that point. So if I know the code and I'm writing the code and I inject that particular conditional, if that condition is true, then do one operation, that operation will always be executed. And this is exactly what is expected in the word count. But what about the other two in red? Those will never be executed because those predicates are always false in all possible executions. And then in the if branch and else branch, I can put inside fake dependencies. So I can put inside assignments of variables that will never be executed. The reason that the program dependency graph is built statically produce that now the slicing criterion for the number of line produce a way bigger slice. So I have a way bigger slice and look for number of words. That's the size of the number of words. So you see, I mean, by adding dependencies that are fake dependencies, my algorithm cannot reproduce a smaller code as output, but is obliged to generate a larger code. In the worst case, it will reproduce the same code. It gets an input. That means making slicing completely harmless. So what are the ingredients for doing all this? So in order to have a, let's say, formal method perspective over this kind of approach to security, how to secure the code here means looking for bugs. This is program analysis, but can also mean, okay, I transform the code in such a way that I cannot do any reverse engineering of that code by using any tool. And okay, so I need some model. So typically the standard model is the one given by Turing, Gödel, and all the big names in semantics. So the semantics of my program is denoted with these fat brackets around fat parentheses around P. And if you imagine that the time of execution, so all the traces of execution for each possible input you have on the Y axis, and on the X, you have the execution that runs in time. Of course, properties of programs are typically undecidable, so we cannot produce tools that decide whether a program is correct, whether it has a bug or not, and so on. So this is standard knowledge in computer science, and in particular in theory of computation. Okay, so this is what happened in the real program. And how can I analyze this? Well, there are many ways for doing it. The first one is I stop after a while. So I stop my computation. I want to see if there is a bug or if an invariant is true. Of course, if I stop the computation at some point, this is somehow called partial execution. So you have an execution that is only up to some point. Of course, you won't be able to find a bug if the bug happens later. So this is a very cheap, efficient, but pretty unsound. The program is still buggy. So you have also testing. Testing is something that can be useful. Engineers do a lot of testing. It's pretty good for physical devices. For programs, it's more tricky because programs have a semantical model, which is a mathematical model. So in principle, you shouldn't use testing, but you should use induction to prove properties of programs. But still with testing, you can test the absence of bugs or whether some property holds, but you are not sure that this may hold for all possible inputs or for possible inputs within a sufficiently large set. This is also efficient, but still unsound. So this comes the idea of Patrick and Radia Kuzo that you mentioned before, Prakash, when you said I spent my postdoc there, and they introduced it in the end of the 70s, so it's pretty old now. It's near 50 years of abstract interpretation. In France, they introduced the notion of approximation and abstraction in the semantics. I try to give you an idea on how it works, the abstraction in semantics. Imagine that the properties of your execution are those shapes. These are geometrical shapes in space. So you have stars, you have ellipsoid, squares, rectangles, and triangles, and octagons. Good. So imagine that your program, so the programs you want to analyze, compute one of those shapes. So that means that the states, the invariant, is described as a set of points inside of one of those shapes. There are too many shapes. So the point is, how can I approximate them? So if I want to see among all those shapes, only whether the computed programs, the computed states are inside the circle, I don't need all those shapes. I just need circles. So I simplify my domain with a domain of just circles. And the idea of this is, okay, I gave up with the possibility of having a complete, exact description of what's happening in my program. I can produce anyway an answer, and the answer is a sphere, a circle, that bounds my states within some region. So I get an abstraction. This is exactly the function that takes a generic shape and produce the corresponding circle is the abstraction function. So can I compute over this abstract domain? This is the abstract domain of circles, and in such a way produce an over approximation of what's happening in the real domain of computation? Yes, the answer is yes. So imagine that you have your program. Okay, you can run, for instance, in this case, each single bullet, a single dot in the picture is one state computed by my program, starting from the left, going to the right for each computational trace. Okay, imagine that you don't want all those numbers, you just want the interval. And the interval is the segment in green that contains those points. One way for approximating is that you run the real program, and at each time in memory, you collect, together with the numbers computed, also the interval, which is nothing else than the minimum and the maximum you computed so far. And you keep going this way. Okay, this is not abstract interpretation. Why I said this? Because this is exactly abstracting the real computation. So we are not using here the approximated object, sphere, circle, the interval, has an inductive invariant. We are still computing the real one, the real output, and then keep in memory the minimum and the maximum. This, of course, is the best way possible to have an approximation, because you are actually not approximating, you are just collecting the intervals at each step. And you are able to see if there is bug or there are no bugs in an easy way. The point is that this doesn't scale. So what's the idea of abstract interpretation, which is not abstracting the real computation, but is using the abstraction of each step as an invariant for the next. So imagine that you start from that interval. Okay, so that's an interval. Then you do one computation, but that computation will start not only from the dots, but also from the points in between the dots within the interval. And then you get that correspond to all this. And from all of them, because you have all the dots between the intervals. So this confuses completely all possible executions. So all possible next steps of the second step produce a lot of spurious possible traces. And now I do the third step, and the third step produce that spurious traces. If I join all of them, I get that. And this is a fixed point. In 3 steps, I produce a fixed point. What's happening here? This is definitely affordable. Abstract interpretation is affordable. It's using the induction with the abstract objects in the computation. This comes back to 1977 in a fundamental popular paper, which is actually the most cited paper in programming languages nowadays. So it's still a very important piece of work. What's happening here in abstract interpretation with respect to the previous case that was not an abstract interpretation? It happens that, of course, you get all true alarms. You get it. But you may have false alarms. So the presence of false alarms depend upon the fact that while you compute, you are not computing over the real states, real executed states, but you use the previous approximation as your intermediate state for computing the next. And in the previous one, there are spurious elements that are not really reached by the program, that are used for the next computation. So this may lead to generate false alarms or false positives. And of course, I mean, if you say that your program doesn't have at all alarms, you are sure that your program is correct. But if it has an alarm, you need to be careful. It can be a true alarm, so the program can have really a bug, or the program can be still correct because the alarm was false. So in general, the inequality that you find at the bottom of the slide is the key point of soundness. It means that the abstract interpretation always contains is an over-approximation because of this spurious information that is injected in the computation of the approximation of the concrete one. So it's sound, so let's see this. So imagine that what you want to prove is if your program satisfies that specification, the specification is a circle. Your program computes a very weird picture and very weird shape. Then you approximate that into a circle. And this is not abstract interpretation. This is the abstracting the real computation. This is the closest circle that contains what P computes. What's happening in abstract, so in this case, you can say, that's fine. You are outside the box. And if you are able to contain, because of the spurious information, everything inside the specification, you are still sure that your original code is safe. So it respects the specification, so it has no bugs. The problem is that it may well happen that due to those spurious information, you get incompleteness. So the approximated semantics, which is the abstract interpretation, gets so big, becomes so big, that goes beyond the specification into the alarms. And this is a case of false alarm. And this happened when actually in the previous inequality, in the previous inclusion, you have a strict inequality. Okay, so it's possible to, if you have an abstraction, it's always possible to refine the abstraction and remove all the spurious information. And this is a paper that we published in the Journal of ACM 25 years ago, actually, with two of my students. So there is always a possibility of finding the best abstraction, which is that alpha function, that makes that inequality an equality. So it becomes an inequality. So you have exactly, you are mimicking exactly in the abstract what's happening in the concrete. It's more interesting from the side of security. What's happened if you twist instead of the abstraction, so you change the abstraction, if you change the code? And this is very interesting what's happening here. This is something that it happened that I can show you, because the same program, you know, there are infinitely many programs that produce the same answer. So you can see on the left-hand side, the Fibonacci function, very simple. And on the right-hand side, a very complicated function that produces the same result as Fibonacci. That has been generated by a code obfuscator developed in Data, where I spent my sabbatical about 10 years ago. It's very, you can see that those two programs are totally different. And it's very hard to understand that program on the right with respect to the one on the left. That program on the right is an example of obfuscation. And actually, if you try to hack that code, you will discover that it will produce Fibonacci, but you will never see the same trace again each time you run it, because they are flipping of random numbers. It's a very complicated execution. But still, it computes Fibonacci. So why this is related to completeness and incompleteness of program analysis? Something very deep happens inside when you analyze programs. If you go back to your old years where students were studying theory of computation, you know that there exists a standard model of computable functions. So programs are associated with functions. And this beautiful world where you have compositionality, extensionality, referential transparency. So everything is so beautiful. And there is a friend of mine from University of Bologna, Simone Martini, that says, well, the standard model is to computer science, so that model of computing like functions is to computer science what movement without friction is to mechanics. This very beautiful sentence that from my point of view says exactly and precisely that when you go into the real world, something weird happens. So you cannot anymore see programs as functions. You need to have some friction. For instance, complexity. Complexity, you have two programs, bubble sort, heap sort. They produce the same sorting, but they run in a different complexity. So complexity is something that is the real world. It's not just, it's intentional, we would say. And very similar to complexity, phenomena similar to complexity happen when you consider program analysis. The problem is program equivalence. So two programs are considered equivalent if they compute the same function. This is the classical standard model. So if they have the same semantics. Good. What's happened when we abstract that semantics? How does the precision of the abstraction affect the program equivalent? This is the point. And we see the following by an example. Take these two programs. These two programs are computed exactly the same. At the end, they compute x equals 0. So the invariant that can be obtained at the end is the same. Okay, so we run that into an abstract interpreter. So this is a little experiment. We run that in an abstract interpreter where the abstract interpreter runs over intervals. So I run that, say, compute the intervals, then I produce the interval. At the end, when the guard is false, something happens that in the very first program, I get exactly the answer. So the very first program is complete. So the abstract interpreter that runs the program into intervals produces exactly 0, 0. But in the second case, because the intervals contains all the points between 0 and 10, and also 1, when you intersect that with the negation of the guard, so you exit the loop, you get the spurious point, which is 0, 1. So the two programs are equivalent in the real world, but they are different from the point of view of abstract semantics. So they are different from the point of view of program analysis. So program analysis may see different programs that are equivalent. This is complete, this is incomplete. But look what happened. Take these two programs now. These two programs compute two different functions. One computes 1, the second computes 0 with that input. So no matter what input x I get, so actually the first program is the constant 1, the second is the constant 0. I run the same analysis. And now I produce exactly the same code, the same output. So two different programs that are different in the real, they are viewed as equivalent in program analysis. Why this? Because once again, because of spurious points, the abstract interpreter, so the program analysis produce spurious elements that make the two outputs the same. In this case, they are equivalent because the program analysis is in both cases incomplete. So actually, program analysis cannot really distinguish program equivalence at all. And here exactly comes the friction. So we cannot use the standard model of functions to reason about programs when we look at them from the point of view of an attacker that uses program analysis tools like a slicer, like a debugger, like a program analysis for dependencies, and so on. So in order to have a picture of all of this and try to see what can we do, because when you do theory, you basically try to figure out what you can and what you cannot do about something. Complexity is an example, computability is another example. So we try to in a series of papers that we published in Popl in the last 10 years, we try to figure out what's happening if we take the set of all programs and we look at and we fix one analysis, one particular analysis, slicing, for instance. So my alpha here is slicing, and I collect in one class all the programs for which that analysis is complete. And of course, the complement of this set is the set of all programs for which that analysis is incomplete. Obfuscating is nothing else than moving from the class of completeness into the class of incompleteness, and vice versa. Deobfuscating is moving on the other way around. So if I have an analysis, moving from right to left means obfuscating my code. So generating a code for which my analysis is imprecise. Going from left to right means removing that imprecision and produce from my code exactly the good code that can be perfectly analyzed. So we can take the set of all programs and split it in two blocks. The obscure side on the left is the set of incomplete ones. The clean side is the set of complete ones. Okay, good. So now let's see what are these sets. So the first thing we can say that if you do nothing, the programs that do nothing can be analyzed precisely. So there are infinitely many programs in the set of complete ones. Of course, this is standard padding. And then this set is So all the programs can be completely understood and completely analyzed if and only if either I see nothing or I see everything. This is an interesting result. So the obscure part disappears. So that means that my program analysis is able to catch all the information about all possible programs in a Turing-complete programming language, if and only if my program analysis is straightforward. If you remember from theory of computation, this looks like somehow Rice theorem for a kind of Rice theorem for program analysis. I want to give you a little proof of this. I try to make it graphical, and you will see that everything that happens in the proof looks like pretty much the fake predicates, the opaque predicates that I was adding to foil, to break program slicing. So let's try to prove this. So one implication is obvious. If you see nothing, of course, everything collapsed to I don't know. So you are precise. I mean, with respect to the question, I don't care, the answer, I don't know, is fine. I mean, it's absolutely precise. On the other side, if your abstraction is the identity, lambda x dot x, then that means that you are not abstracting anything. So the real computation is exactly corresponds one-to-one to the abstract one. So that implication is obvious. It's more tricky with that other implication. So imagine that your set of space is the power set of all possible states computed by your program, and the properties are all those bubbles. So each bubble is a set of those states. This is our space of program properties. So a property of my program is one of those bubbles. So imagine that your abstraction is not the identity. What does it mean? It means that there exists a bubble S, which actually a set S, that cannot be approximated by any bubble, abstract bubble. So there exists a point C that escapes that S, and that C is introduced because of the approximation. This comes from the fact that the abstraction is not the identity. Otherwise, if it was the identity, it was able to represent exactly the set S. So C exists because the abstraction is not the identity. And because it's not the top, so it's not everything, there exists a bubble that is smaller than everything. So there exists a B that escapes one bubble. And now we will exploit those 2 points, C and B, to build a program that cannot be analyzed by alpha. And the program is very simple. You simply input x, so that is a program, it's a function. If x is equal to C, then you go to B. Otherwise, you loop forever. So what's going on here? Okay, if you run that program, the first line, if you run that program on the real input, what you get is that you loop forever because C will never be, is not inside S. You loop forever, so it's bottom. If you run the program on the abstraction of S, then you introduce C, and because of that, that program will trigger by C the activation of B, and will produce B, and B is different than empty set because there is 1 point. So that program escape the class of those that are complete. Cool. So what can you bring home from this? That whenever we can see something, but not everything, in my program analysis tool, so any algorithm that can see something, of course, it has to be to see something, otherwise it's useless, but not everything, and of course, it has to get rid something because otherwise the properties are undecidable. There always exists a program for which we cannot be precise. Interestingly, we can try to figure out how to transform these programs. So can we compile a program from one class to the other and vice versa? So I'm collecting here the so-called clique, the set of all programs that are equivalent to a given program P. So those that are complete too. So these are the versions of P that are complete are the completeness clique. The version of P that are incomplete are the incompleteness clique. So the question here, can we move from one to the other? So given a program, can I remove the mess that is introduced by obfuscation, this is one question. The second one, given a program, can I obfuscate that by making it incomplete? Okay, so the first thing that we can see is that anyway, no matter what program, if I keep padding with nothing, I can generate infinitely many versions of that program. And if P is complete, then that set is complete. And the second stuff, which is interesting, is that the same happened on the incompleteness one. You take, if there is a P incomplete, then I can keep padding. Let's see the compiler. So given a complete program, can I transform it into an obscured one? Yes, I use exactly the same trick as before. I have a set as the approximation producer. This is the approximation. It produces a point that was the C point in the previous proof. And then there is a B point outside. Then I produce a predicate, and the predicate is my input inside X? If I run this predicate, of course, in the approximated, so with the input which comes from the inductive invariance computed so far in the abstract domain, I generate spurious traces that depends on that point C. And then this may trigger a dead code. So I can put in the dead code all the mess I want, like for instance, fake dependencies as I did in the beginning, and then I foil completely program slicing. This transformation exists, so I can compile any program into an equivalent one from completeness to incompleteness. Question, can we do the other way around? Can you remove incompleteness and produce a complete one? No, it's enough two-point domain. If you have an abstraction that simply has a bottom which corresponds no termination, and I don't know, this domain has just 2 points, so all fixed point computation in abstract interpretation in two-point domain converge finitely. So if you are complete here, it means that if it terminates, you are able to see it. If it doesn't terminate, you are able to see it. So because the abstract interpreter terminates in answering this question, you would make termination decidable, which is impossible. So you cannot, in general, transform an obscured code into a clean code by a program compiler. How about interference? And then I go towards the conclusion. So interference is something that fits inside this way of viewing things. And to do this, I will go backwards, let's say, towards about 20 years ago when we started the problem of interference. So Gauguin Messeguer in 1984 introduced the notion of interference. You have a secret. So let's go back to this point. So far, we've seen that we can transform the code and obscure the code, and we can transform the code and make it clean the code. The first one can always be done by compilation. The second cannot be done in general. We've seen that understanding how the program works through an algorithm is something that is related to the problem of decidability, so has strong limitations. And this can always be done for straightforward properties, so it's generally for useless analysis. And because of this, it is always possible to obfuscate code. So now the question is how interference and information flow can be modeled within this way of thinking of this framework. So let's go to Gauguin Messeguer in 1984. So the idea was that you have a piece of program, you have your code, you have secret data, you have public information, and there is no information leakage if you don't have any flow that you can see as an external observer from the secret H, from the secret information to the public one. So by watching just the public, so you just are able to see what's happening in the public, you cannot get any variation, any change, understand any change of the secret information. So of course we do abstract interpretation, so we were interested, actually this notion is pretty strong because this holds if you basically can slice out the piece that manage the secret part from the public one. So the condition of non-interference holds rarely in programs because programs manipulate data and let's say that possible information flows can happen easily, even if in particular, these are not so problematic from the point of view of security. So the question is, can we weaken this notion? So in order to weaken this notion, we need to ask the following question: who observes the information flow? So is it an observer that see all data or can see properties of data? So it has a lens in front of his eyes, and that lens produce an approximation. And what information is allowed or is not allowed to flow? And this is the notion of abstract non-interference that we introduced in 2004 and fits exactly in this framework that I showed you before. Again, you have secret and public, and there is a flow if the external observer can see a flow from secret to public by watching the public. But watch out, now the observer is an abstraction, so it cannot see the shapes of stars and rectangles and octagons. It can only see, for instance, circles. So it has a limited power of observation. And the same, the secret that flows can be itself a property. Also, what is allowed to flow up to the observer can be not just the real value, but a property of the value. And this is something that happens when we attack a system, for instance, a cryptographic protocol. So let's see how it works. This is the standard equation in Guggen-Meseguer non-interference. So you have the public input, the private input in blue, and the public observer. And you change the private, and you don't want to see any change in the public in running your code. But if you change the public input, you may change the public, but still any further changes of the private won't produce any answer, any change in the public. This is non-interference. What's happening in abstract non-interference? So there are many ways for abstracting. Of course, now the abstraction is a kind of partition of my state. So if I move inside the partition, you see that I'm moving inside the partition the public. Any change, real change in the private, will remain inside the same partition in the public. That means that essentially I cannot see a change in the property. And this corresponds exactly to that equation below. Of course, if you change the public input, you may change your property as the output, and still any change will remain inside the property if you move the private input. You see that this is a weaker form of interference. And this is the very first, but you see that I'm abstracting the output. So if you look carefully at the equation is has only an abstraction in the output. Here you may have deceptive flows. Deceptive flows means that, for instance, any change, I will see that, we'll see that in a minute with an example, it's clearly. Now, instead of making just the abstraction of the output, I let the whole property to flow into the computation. And this is a further weaker version of my system. You see that in this case, the property, if I change the private input, flowing completely the property of the public input into my program, I remain inside those two regions. If I change the property in input, I remain in those two other regions. And here the abstraction eta in red is inserted inside. So here we are doing real abstract interpretation. So now standard interference corresponds to having the identity in input and out. This is just Guggen-Meseguer. For instance, if you see here, you change H, you leave L equal to 1, and you can see as the output a change in L. So that means that there is an information flow from private H into public L. And this exactly is a case of violation of interference. Then we have the very first one. The very first one is now I just see the parity of my output. In this case, a change in the private information won't leak into the parity of the output because I always keep watching just an odd value. So you see that this the weaker version that we introduced, the first one, is already weaker than standard non-interference. You may have deceptive flows because what's happening here? Because the fact that you have equal parity, so both 4 and -4 are both even, so from the property of parity, the public is equal, and there is no change in the private, h is equal to 1 in both cases, you see a change at the end, and this is a deceptive flow. So that definition, the very first, without the abstraction inside, so not the real abstract interpretation, but the abstraction of the interpreter, may produce deceptive flows, and this is not good. Instead, the one that I show you, where you see those red arrows that I'm pointing, are the abstraction plugged inside the computation. So this is abstract interpretation. We use the abstract values to compute the next step. This doesn't have deceptive flows. And you see that in this case, you have an even weaker notion because even if there is a change in the private information, -3 and 1, you see that the outside, so the observer on the public side, that just see the sign, can see nothing. So it doesn't see nothing, so it doesn't see any change. So this, in a way, is a way for weakening that information. So if the observer just see the sign of the output, that piece of code, even if there is a clear dependency inside from H to L, is secure. So why all this fits into completeness? Because Josh and Lino many years ago introduced a framework where they're saying you have security when you can basically you can see those two programs HH, PHH equal to PHH. What is HH? It's nothing else than an abstraction. It produces all possible values over, so it confuses all possible values, producing as output all possible values in the private side, and is the identity in the public one. This is exactly, if I compose this as functions, you see, this is exactly the equation of completeness. So security corresponds to a case of completeness. And this is pretty interesting because we can apply all the previous results I've shown you to the case of information flow. And moreover, I can also look at what is not allowed to flow inside. So the property phi that is from the private that is not allowed to flow in my code. And this happens if I change the partition in phi and I remain within the same two blocks in the output, I don't have phi to allow to flow into the external observation. Okay, so and I conclude with this slide, and then I just do the conclusions at the end. And we have abstract interference, which is the second line, is exactly an equation of completeness. So what can we conclude from this? What are the conclusions? Non-trivial analysis can always be foiled. So the only trivial ones cannot be foiled, okay? So they reveal properties about the way the code executes and the code is written. And this makes program analysis pretty much similar to computational complexity. It is always possible to transform a program into an equivalent one, exposing deceptive flows by that compilation I did. That's it.
Very interesting, very theoretical, but I think it very interesting
Thank
how
you.
formal methods and how, I'm just trying to digest to see. Maybe I'll wait for Q&A people to ask questions, and maybe I'll start with a couple of questions. I think it's fascinating what you're talking. I do enjoy the portion when you talked about, and when we talk about cybersecurity, when each one has their own lens, whether,
Yeah.
who is the observer, right? And or who is the non-observer. And so the question goes back to you in a sense, how do you see when we have all AI-driven solutions are taking place in all kinds of systems and critical infrastructures, and what is the future that holds for formal methods when we talk about security in the terms of approximation, and it's always going to be there is some incompleteness. And how do you see the computational trade-off that one has to compute to deploy these formal solutions in devices and subsystems,
Yeah.
And it's a very broad question, but I want to just pull up your thought in actually the AIs or LLMs that are getting attention, and how do you see the deployment of formal methods in there's always this is a very this area has been there for many years in approximation solutions, right? I think,
Yeah.
and but I'm more like a practical guy, but I'm still trying to understand to see what is your perspectives on where are we right now in terms of deploying solutions at device levels or systems levels in making sure we see these different lenses, these different approximations, so we know how to model that.
Yeah, so we are obliged to use lenses because the real world is too complicated. In particular, the world of software is too complicated. In particular, if we want to analyze large language model and their fairness and produce proofs of fair behavior of these extremely complicated tools that have billions of variables inside. So imagine that the information flow explodes exponentially on the number of variables and parameters. Imagine what's happening in a large language model of the size of billions of elements. So we need lenses, we need approximation. And the challenge is to find the right one. But actually finding the best approximation correspond to have a full understanding of the system. And nowadays, these systems are mostly black box or nearly black box. So we treat those systems as biological entity. We don't know the cell. So what do we do with the cell? We put something around the cell and we see how it reacts because we don't know the cell. We didn't create life. So, so and it looks like that the approach to these models and these extremely complicated systems is changing and is borrowing approaches from natural science more than from mathematics. I still believe that instead you can use those systems to help deducing the right abstraction. So using an AI system that analyze a lot of code and tries to produce the shapes and the invariants that can be used in the abstraction is an extremely good help for achieving the right abstraction, for catching the right abstraction for a family of programs. So I think that in the future, after people that do theory, people that do formal method will use and will exploit a lot those tools as a companion into the design of the abstraction. Because in the end, when you deliver your code, you want a proof of correctness. A code that is almost secure, almost correct, doesn't make much sense. If it produces hallucinations and this correspond to bugs, this can be completely useless, even can be very bad for your company if you deliver code like that. You want a proof of correctness, but this can be very hard to achieve, and you can use AI models to produce the invariant, to help generating the proof. And this is, I see the future as a combination of these two words. Nowadays, we were forced not to have those tools because we were running a dynamic analysis, and you see, oh, the shape looks like a circle, so probably we need to generate a domain of circles in order to approximate the invariant. You can do the first step by AI, and I think it can be very helpful.
Oh, I think, let's see. We have a question here. Okay. Thank you for the presentation. Probably related to the previous question, but could you comment more on how traditional non-interference principles be applied practically, more quantitative measures to protect machine learning model privacy?
Oh yeah, I think that I think that in the standard model, the standard definition of non-interference simply does not work because it's too strong. And if you apply that into a machine learning model and you want to see if there is no information leakage, that standard definition of non-interference cannot simply apply because any method for proving it, any method for proving it will fail because there are infinite, I would say, an exponential number of possible dependencies inside. So you need to find, I think that absolute interference is the best way for doing it because you prune out something that you don't, you, you have the feeling that is not necessary. How to prove it? Once again, you need to find the appropriate lenses to put between the dependencies in order to filter out what is useless. How this will scale, I think nowadays it doesn't, because I mean, you need to open the box and go propagate inside all these information and moving all the information through all these lenses inside a very complicated machine. It would be very interesting once again to find probably non-sound, but soundy methods that can produce some proof of reliability for these tools.
I have a very general question. In terms of the search space for when we look at this approximation word, I think how do you see the computational overhead of running these formal methods? Do you think, the trade-off between running and when you talk about completeness and security, is computational burden? How do you see the computational burden for deploying these approximation solutions? If so, would you prefer to do at a lower level, device level, or do you go at a network level or systems level? What would be your perspective thought when people are,
Oh, I
yeah.
think that these tools need to be, well, I'm not a software engineer skilled in such a way to figure out how this method can scale up to the whole stack of on which a system is designed. They are moving upwards. They are moving up more and more because of two reasons. Power of computation is increasing. AI methods helps you, so it's a good trade-off. It's a very good interface between formal methods and AI. There is beautiful possibilities of development. And this will help scaling up and moving up into the stack, all these methods. The ideal would be to have in the end that any software you produce, either generated by a machine like an AI-assisted copilot, or by a bunch of programmers, or by a combination of these, is always followed by a proof of correctness. That would be an ideal thing. I think that it will probably never happen. But even approximate or just, let's say, parts of these proofs can be used nowadays, and still they are. Airbus, the aircrafts have been most critical part of the Airbus fly-by-wire system has been certified by abstract interpreters. So all the lines of Airbus has this certification, which is an inductive. I mean, Boeing doesn't have it.
And my probably final question in terms of data or information leakage, and we see quantum getting attention, and then this formal methods. And how do you draw the synergy between the interplay between the formal methods and quantum? Do we see, you know,
Yeah.
I don't know.
Yeah,
I'm just
it's a very interesting question because actually I just started a PhD student in my group here that is a very good student and with a very good mathematical skill, and he's studying abstract interpretation in quantum computing, and it's very interesting because we found out similar results like the one I show you that it's almost impossible to have a complete splitting of those entangled states without introducing false alarms. So those states, those quantum computing has an even stronger entanglement, exactly, between states and information flow. and it's even harder to. My question is whether we can have a quantum analyzer of a quantum system. Because so far, everybody tries to analyze a quantum system with the classical computer. And of course, in that case, you cannot avoid false alarms. I mean, we prove it. It's pretty interesting, actually.
Cool. Fascinating. Thank you. I learned a
Thank
lot
you.
today. Appreciate your time. I think we're going to close the webinar, but I think you will receive a nice plaque from UND and a nice
Okay,
letter
thank you
from
very
our
much.
team.
Thank you
Thank
very
you,
much.
Dr. Roberto. We'll be in touch and maybe we'll find some
Sure, please.
once.
Yeah, and moreover, maybe I can come to your place one day. It would be in North Dakota. Is interesting, I think, in the summer probably.
Yes.
Okay,
Take care.
take
Thank you,
care.
Dr.
Bye bye.
Roberto.
Thank you.